All right, let's get started. We are talking about proteins in this video. We're on page 204 of your workbook. And in this video, we are learning a little bit about proteins, specifically how amino acids react to form proteins, how proteins undergo hydrolysis, and what happens when proteins get denatured. So a little bit about reactions. We will also look at the structure of proteins, specifically the primary, secondary, and tertiary levels of protein structure. To get started, I'd like to remind you what we said in the previous video, which was this: amino acids are the building blocks of proteins. That idea will help make sense of these reactions we're about to look at, amino acids undergoing condensation. That's what we left with in the previous video, and as we'll be building toward the end of this video is the big idea I've listed here. The three-dimensional shape of proteins is what determines their function. So those are some ideas that we'll be looking at here. Let's start with amino acid condensation. And before we even do that, I'm going to give you a quick reminder of what does an amino acid look like. Amino acids, as we saw in the previous video, their structure has carbon at the center. Carbon, of course, makes 4 bonds. The word amino acid helps you with the structure. This part of the word amino means amine. And in the same way that this is written left to right, amino acid, we'll draw it left to right, amino acid, as if we're writing the word. Here's amine for the amino part of the word. Here's acid for the acid part of the word. So amine and carboxylic acid. This third position is always a hydrogen, and it's the fourth position that is different from one amino acid to the next. We refer to that fourth position as the side chain. I should let you know that I could put the side chain on the bottom and then put the H on the top. Those two can be interchanged, but it's always consistent. You should always draw it so that amine is on the left, carboxylic acid is on the right, as we've done here. So what does it mean for these amino acids to be the building blocks of proteins? Let's take a look at what that reaction looks like. And you should recognize that condensation is a reaction that you've seen before. You've seen that in how fatty acids and glycerol react. They undergo condensation. You've seen it in how monosaccharides undergo condensation. You initially saw it when you were forming esters. A carboxylic acid and an alcohol react in a condensation reaction. So luckily, this is not a new reaction for you. I'm going to turn the paper over, actually two pages away to page 205. Here's where we see examples of this condensation, amino acid condensation reaction. We will look here. This is a complete the reaction exercise for us. This, as you know, is an amino acid. I see carbon in the center, amine, carboxylic acid, H, and the side chain. Here's another amino acid, amine, carboxylic acid, H in the side chain. What will happen in the condensation reaction, it's the same thing that happens in any condensation reaction that you do. Box out water and then slide the two pieces together. The boxed out water tells me that water will be a product. So I'll say that H2O for sure will be a product. But the main product we're interested in is what happens to the fragments from the amino acid. As you know from doing this reaction, this condensation reaction so many times before, you know that when you box out water, H and OH, nothing else changes. Everything outside the box stays exactly as it was before. So we will draw it exactly as it was before. This is what I'm doing here. Here's the HHN. Then there's carbon with H and a methyl group. And let's see what's next. Then I need a carbon double bonded to O. And then what's next? The O is gone, the H is gone, the H is gone. So this carbon will be now connected to the N. That's my new bond. I was right here. carbon. It's bonded to the double bond O, there that is. But then when I keep going here, O is gone, H is gone, H is gone. What's next? N. And then everything else from there stays the same. N is bonded to H, and then a carbon with 2 H's, and then the carboxylic acid group. So what we just did is we combined 2 amino acids. Condensation means combine, to get a larger molecule. That larger molecule is called a dipeptide. It's kind of like a diamino acid. So peptide is just another word for amino acid, but you won't ever see diamino acid. You'll just see dipeptide. You might see peptide plus peptide to make a dipeptide or amino acid, but this will be called a dipeptide because it includes 2. We made it from combining 2 amino acids. Where's the new bond? The new bond is right here. And that new bond is called a, not surprisingly, this is the new peptide bond. We've seen several different names of bonds with this condensation reaction. When we were in carbohydrates, we called that new bond a glycosidic bond. When we were in esters and then lipids, we called that an ester bond. This is called a peptide bond. A single amino acid does not have a peptide bond because it has not yet done any combining. But when I take one and combine it with another one, I get a double. I'll call that double a dipeptide, and it has a peptide bond. Up at the top, there was a couple of examples to show the same thing. Here's a single amino acid. Here's another single amino acid. They're combining by boxing out water. So this is a single amino acid. Here's another single amino acid. And when they undergo condensation, we get a dipeptide that's formed because it's formed from 2 amino acids, and here's the new peptide bond right there. That peptide bond is formed when you combine those 2 amino acids. You should pause the video now, pause the video and see what happens when you let these 2 amino acids undergo condensation. Why don't you pause the video and see if you can draw this out on your own. Now that you're back, hopefully that did not give you trouble, but if it did, let's do it together. You know that you will box out water. That's what condensation is. OH and H. It doesn't matter if you box out this OH with H here or the OH with H up there, you'll get the same structure. I know that one of the products will be the water from boxing out water. The other will be everything outside the box will connect with the other fragment. So this was HHN, so nitrogen with 2 H's, connected to a carbon with 2 H's, and that's connected to a carbon with a double bond O. But after that, the O is gone, the H is gone, that H is gone, and now we are connected to a nitrogen with 1 H, a carbon with an H and a methyl, and then the carboxylic acid. So this is our dipeptide. And if we want to, we can highlight that peptide bond. That's the new peptide bond. I'm making a point of highlighting that peptide bond because it's important for you to be able to identify it. We'll see very soon that that peptide bond is the thing that breaks when we undergo hydrolysis. What we've just done, I'd like to come back to the outcomes that we're talking about. This video was learning how to predict products and draw structures for amino acid condensation, protein hydrolysis, and then we'll be talking about protein denaturing. What we've just done is the amino acid condensation. And what we'll talk about next then is hydrolysis. Before we can do that though, I'd like us to talk about what is a protein. We mentioned that amino acids are the building blocks of proteins. We also mentioned, I'm going to slide that up a bit. We mentioned this when you do condensation between 2 amino acids. So amino acid plus amino acid, you form a dipeptide plus water. That's the reaction that we just saw. What happens if you have 3 amino acids? This was 2 amino acids. What if you have 3 amino acids? Then you'll get what we would call a tripeptide. What if you had, let's make this up, what if you had 17 amino acids combining one after another in the condensation reaction? We don't have a prefix that stands for 17, but that would be called a polypeptide. And you always have one less water. 2 amino acids gives 1 water, 3 amino acids gives 2, and so on. But this is our focus. 2 amino acids, dipeptide, 3 would be a tripeptide. More than 3 even, we would just call a polypeptide. But what is a protein? A protein is formed when you have at least, we'll say 35 to 40. It's not a hard and fast magic number, but you need a lot. 35 or 40 amino acids. This would be, 17 would be considered a polypeptide. It needs to be 35 or 40 to be considered a protein. And this would in fact be a small protein. Many proteins consist of hundreds of amino acids. So proteins are big. A protein formed from 40 or 50 amino acids, that would count as a protein, but it would be considered a very small protein. Most proteins are hundreds of amino acids. So a dipeptide and a tripeptide are 2 and 3 amino acids. You need 35, 40, somewhere in that ballpark to be considered a protein. So then, knowing that, what is protein hydrolysis? We can take advantage of the fact that you know already that hydrolysis is just the opposite of condensation. So we could do this. We could say, aha, if this is a dipeptide, what happens when this undergoes hydrolysis? That's just the reverse of condensation. So when dipeptide undergoes hydrolysis, a dipeptide plus water doing hydrolysis gets us back to the 2 separate amino acids. So hydrolysis is still what it always has been, the reverse of condensation. You break the bond. So in this case, with hydrolysis of a dipeptide, you break the peptide bond. Same as above, hydrolysis of the dipeptide breaks the peptide bond. What would happen when this undergoes hydrolysis? If I asked you to complete this reaction, it starts getting to be a lot of drawing and writing, but the main thing is making sure you understand the concept. Can this undergo hydrolysis? And in fact, what is this? It's not a protein. It definitely is too small to be a protein. It's not 30 or 40 or 50 amino acids. What is it? Let's find the peptide bonds. I see a peptide bond here and I see one here. I see 2 peptide bonds. I'll highlight them for you. 2 peptide bonds indicates that this must have been 3 amino acids that combined. I can, if I want to, also say what are the side chains that were formed or used to form this amino acid. And I see these 3 side chains. How do I know that's the side chain? Remember, all the way back to what an amino acid looks like. The carbon that's next door to the amino acid has an H in a side chain. So here was the amino acid, H in a side chain. This came from the amino acid, the carbon double bond O, H and side chain, carbon double bond O, H and side chain. So I see 3 side chains, 2 peptide bonds. This means that this is a tripeptide. And to remind you, a tripeptide, because how do we know that? Because we see 2 peptide bonds. That's one way that you know it's a tripeptide. And you also see, you can identify or see 3 side chains. I'm going to draw what the products are, although it's going to get very tiny. The main thing is being able to identify what happens. Drawing it is a little bit less important, but it's important to be able to do. So let's do it. Here's the amine, the side chain, so there's one amino acid, amine, H in the side chain. Here's this side chain. And the third amino acid will be amine, carboxylic acid, H in the side chain, this long side chain, like so. So 3 separate amino acids. That concept is the main thing. The drawing is our secondary focus. The concept is the primary focus. What happens when a tripeptide undergoes hydrolysis? You'll get 3 separate amino acids. What I'd like you to practice on this one, I'm going to have you pause the video. I'd like you to take a highlighter and highlight the peptide bonds. If you don't have a highlighter, then circle them. So pause the video and identify the peptide bonds. Now that you've had a chance to do that, I will do it with you. Here's a peptide bond, and here's a peptide bond. I only see 2. So this is another tripeptide. If I'd like to highlight the 3 side chains, they're always immediately to the left of that C double bond O. So immediately to the left of this one, there's the side chain. Here's this carbon double bond O, so immediately to the left of it will be the carbon with the side chain. Carbon double bond O, so immediately to the left of that will be the side chain. I'm not going to draw the 3 separate amino acids on this one, but I want you to recognize that that's what you'll get. If you do hydrolysis on this tripeptide, you will get 3 separate amino acids. Likewise, if you have a protein, and it undergoes hydrolysis, what will you get? Remember, protein is as many 50 or as many as hundreds of amino acids. You will get lots of amino acids then when it undergoes hydrolysis. Anywhere from 35 to hundreds. It depends on how big the protein is. Anywhere from 35 amino acids to hundreds of amino acids, depending on how big that particular protein was. This last topic, so what we've just done is talked about protein hydrolysis. The peptide bond breaks to reform the amino acids. That's what protein hydrolysis is. This last topic of protein denaturing, it goes along with this idea of identifying primary, secondary, tertiary levels of protein structure, and it helps us understand why is it that proteins have to have 35 or 40 amino acids at least. Why is that? And to explain it, I'm going to ask you to come with me to page 207. 207 is showing different levels of protein structure. And here's the words that go with the symbols we saw a moment ago. Primary structure is abbreviated this way. You've seen this before. Secondary structure is indicated with a 2 degree. Tertiary is this. What are the primary, secondary, and tertiary levels of protein structure? Here it's showing it in pictures. The primary structure is just the order, the sequence or the order of the amino acids. In other words, here's an alanine followed by a leucine, followed by a serine, and so on. What's the order of amino acids? That's the primary structure. Remember what the word primary means? It means kind of like the main, like your primary address is your main address. The primary structure is what's the main structure of the amino acid. How was it built? It's built by connecting one amino acid after another, after another, after another, as we saw just now. And that order or sequence is called the primary structure. I'm going to write something here because I want to make sure that you have it. Hydrolysis will change this. Right? Remember, hydrolysis is like scissors. So if you break a peptide bond, each of these connectors is a peptide bond. If you do hydrolysis and break a peptide bond, now you don't have the same order anymore. You have a different order. So hydrolysis will change that primary structure. But what's secondary and tertiary structure? Most proteins don't stay as their structure does not, 3D structure does not stay as just kind of a long string like this. Instead, it's fairly common that the string organizes itself into a particular repeating pattern. And I'd like to focus on the helix. The helix, which looks like I don't want to say coil because there's this random coil. I'll say it's an organized coil. That kind of spiral coil. Looks like a spiral. This is a common one. The accordion type thing is one, but let's not focus on that. The random coil might be the case for some proteins. We'll use this as our example, that spiral coil. Many proteins coil themselves after the primary order or structure has been determined by the amino acids bonding. Then that long string coils itself into a spiral, and that spiral is referred to as the secondary structure. It continues to organize itself though, so that the coil itself folds. I'm going to call this folded into a 3D shape. So the spiral or the coil folds itself up into a particular 3D shape. And this shape determines the function of that protein. Much like the shape of the key that you use to get into your apartment or your house determines if it functions in the lock. If you shave off one of those little pointy things on the key, it might not work anymore. Definitely, if you melt it, it won't work anymore. So the 3D shape determines function. Most proteins have a particular 3D shape. And that's called the tertiary structure. What we're not getting into, because we lost 2 weeks of our term, is the why. Why does it do this? Why does it do this? It has almost everything to do with intermolecular attractions among the side chains of the amino acids in that primary structure. So if you want a very short, quick, what's the reason? It's intermolecular forces that determine that coiling and then folding. What is denaturing? Denaturing, and I've slid it down here, denaturing, I think a word that I'd like you to connect that with is unfolding. That's what I'd like you to think denaturing as. Denaturing is unfolding. And as soon as you see that, then I'd like you to recognize, the 3D, the tertiary structure was called the folded structure. So denaturing means unfolding. In other words, destroying the 3D level of structure. If you unfold it, it does not have that 3D shape anymore. And if it does not have the 3D shape, then it does not have the function. And what that means is, I'm going to put these thoughts into a couple different bullets here. No 3D shape. Actually, I'll put different, because it will still have a 3D shape. A different 3D shape means its function will be destroyed or at least damaged. So when you denature a protein, its function is destroyed or at least damaged because you have unfolded it. Its tertiary structure has changed. So hydrolysis changes the primary structure. Denaturing changes the tertiary structure. Denaturing will change that tertiary structure. I'm going to put in parentheses here, sometimes that secondary structure changes when denaturing happens. I'm putting it in parentheses because that's less of our focus. This is what I would like you to focus on. When you denature a protein, you're changing that tertiary structure, that 3-degree structure, and then that changes its function. Denaturing happens when you heat it too much, if you add acid, if you add base. You actually saw this in last week's, well, this week, depending when you did it, the protein lab. The protein that's in milk, it's soluble. You know that because when you drink it, there's no chunks. If there's chunks, stop drinking it, right? So you're drinking milk, you know there's protein in there, but it's soluble. If you add some vinegar to milk, and this lab, you're doing it by looking at pictures, you'll notice that all of a sudden you get like a big glob, you get these curds, and that's the protein that became less soluble. Part of what you did when you added the vinegars, you denatured that protein. You changed the solubility and you denatured it because you added acid. So you can denature by adding acid, you can denature by adding base, you can denature sometimes with alcohol. That's in part how hand sanitizers can work, is denaturing the protein components of viruses and bacteria. You can denature with heavy metals such as silver. And what else did I, oh, I forgot temperature. A high temperature will eventually denature a protein. And you can denature sometimes by physical agitation, such as when you're making whipped cream. So that is what I want you to know about denaturing. I'm going to return to our original page to make sure we've talked about what we wanted to talk about, and we've just finished talking about protein denaturing and primary, secondary, tertiary levels of protein structure. So I encourage you to take a look at the practice problems that go with this topic of proteins and go with those specific objectives for you to learn. Take some practice for that. And then when you're ready, join me for our final video of the week, which will be on enzymes. So we will see you then.